Hello students, welcome to my lecture series on reinforced concrete structures. In this class, I am going to discuss about load carrying capacity of axially loaded short columns. Okay, so let us discuss what are the outcomes of today's class are. After completion of class, you will be able to know what is the effective length of the column and their end condition, and based on the end condition, how to calculate effective length of the column. Those things we discuss here. And the second point in this today's outcome are a load carrying capacity of axially loaded short columns. So how much load it can bear for given dimension of a column. This P value we can calculate. For this P value we have some codal equation. Based on the codal equation, how to calculate that load load carrying capacity of a axially loaded short column. So let us recall the things what we discussed previously in our last class. So we discussed about the definition of column and the pedestal. What is the column? What is the pedestal now? So before that, what is the compression member we have discussed? A compression member is nothing but a RC member which is subjected to a compressive force. Right? This is called a compression member. Right, here our see the column is in a structure here. In which direction it is there? It is in vertical direction. Which direction? Vertical direction. Sorry. So in vertical direction, so the load is acting on this column is say in this direction because of the sulfate of the slab and load which is likely to come on this onto the slab, and we have a reaction force from this ground. So this is a vertical direction and it is subjected to compressive force. That's why this is called a compression member. Now in building or any RC construction, we can call it as a column. And other definition of a column is effective length by LE by least lateral dimension. Say least lateral dimension is D. If it is greater than 3, then we can categorize it as a column. Right? If this LE by your D is less than 3, we can categorize it as a pedestal. Okay, clear? I think you got the difference between the column and the pedestal. Then we discuss about codal recommendations which are going to use for design of a short columns or any column. That is how much longitudinal reinforcement to be provided, and what is the actual definition of a axially loaded column. So in practically we know that the true axially loaded column is not possible, but code has given some provision for that to when we can call a column is a axially loaded column, right? So this is the axis of the column. If the load is acting on the particular axis of the column, then we can call it as a axially loaded column. But code has given if this load acts at a certain eccentricity, that is E is less than or equal to 0.005 times D, then also we can call it as a axially loaded column, and subjected to condition that it should not exceed 20 mm eccentricity, right? It should be less than this and should satisfy this 20 mm criteria also. Then we can call it as a axially loaded column. Okay. Now, if it is exceeding this value, we can call it as a eccentrically loaded column, right? Then the area of tension reinforcement, area of longitudinal reinforcement in columns are provided. Minimum is 0.8% of a gross cross-sectional area of the column. So this is the main reinforcement. Main reinforcement in the column. It should be it should be greater than 0.8% of total gross cross-section of a column, and then it should not exceed 6% of total gross cross-sectional area. But practically we will provide what is that? It should not be more than 4% of gross cross-sectional area. I already explained you why 6%, why 4%. What is why we are using 4% for that? Why not using for 6%? Those things we have discussed in our previous classes. And then we have discussed the spacing between and the stirrup, that tie, and if it is a helical tie, what is the spacing pitch to be maintained, and what is a lateral tie, what is the pitch distance to be maintained. Those things were discussed, and that minimum diameter bar used for this column is 12 mm, minimum diameter bar, and the number of bars required for a square or rectangular column, minimum bars are 4, for a circular column is 6. Those things we have discussed. In today's class, we discuss in detail about effective length of the column. So, effective length of the column. What do you mean by effective length of the column? The definition of the effective length of the column is, the effective length of the column is a distance between points of zero bending moments. So, that point generally call it as a point of contraflexure of a buckled column, right? If you load a column subjected to a load, right, like this, it is tends to buckle in this direction. So at this particular point we have a zero bending moment, and at this particular point we have a zero bending moment. So I can call it as those two are what, point of contraflexure or point of inflection points. So the distance between these two is called as a L effective, right? And this majorly depends upon what, unsupported length of the column, that is the distance between lateral connections. So on which connections this column is connected, and end conditions, that means on which support these columns are mounted, whether it is a free, that means there is no support, or it is a fixed support, or it is a hinged support. Based on this parameter, effective length of the column depends on. So let me discuss in detail about this. Say this is a column, right? If it is subjected to a vertical loading, right, then it will buckles like this. Okay, the distance between these two, when this at this particular point the bending moment is 0, right, and this particular point the bending moment is 0. So the distance between two zero bending moment points are called what? Effective length of the column. So this is termed as effective length of the column, right? But this effective length of the column depends upon end conditions. So those are, sometimes your column may be a free end condition, right? Free end condition, or sometimes it may be hinged, right? Or sometimes it may be fixed. So by considering these, let me explain the concept of what is the end condition and how to calculate effective length of the column. Suppose, let me brief what is the hinged support is, what is the hinged fixed support is, and what is the free is. You know the symbol for hinged support. You might have seen in hinged support practically in your houses. That is, your best example for hinged support is door, where your door is mounting on hinges at various positions along the height of the door. So this is the hinge point. If you apply the load over the door, it will not move in vertical direction, it will not move in horizontal direction, right, but it will rotate in rotate clockwise or anti-clockwise. That means there we have restraint, means resistance of movement in x direction, or I can say horizontal direction and vertical direction, and there is no resistance of movement of a door or a door in your clockwise or anti-clockwise direction by means of providing hinge supported particular location of the door. So if you provide a hinge support at the any one of the end of the column, so they are free to rotate. Okay, they can rotate clockwise or anti-clockwise direction when you apply the load over the column, right? You know the fixed support, right? The best example for fixed support is your any pillars, right? So fixed means it will not have movement along the h direction, that is the horizontal direction, right? It will not move along the vertical direction, and there is no movement along the clockwise or anti-clockwise direction. Take example of building. Suppose it is a building. Will you move horizontally your building? No. Will you move your building vertically? No. It will rotate in any direction? No. Even you apply a load on the building, it will not move in horizontal direction. It will not move in vertical direction. It will not rotate in any clockwise or anti-clockwise direction. So hereafter, what I mean to say is, if a column supported with a fixed support at any one of the end, so that end I can say it is a restraint against the rotation. What I can say here, it will not move x direction, y direction, and what is that, your rotation on the clockwise or anti-clockwise direction. So this end of the column is restrained against the rotation. There is a resistance to rotation that will not move any direction. And suppose your column is hinged at one particular point on one of the end. Here it will not move in horizontal direction, it will not move in vertical direction, but it has a movement in clockwise or anti-clockwise direction because of hinged support. So I can say when the column is supported or the column is having end connection as a hinged connection, then we can say it is not a resistance against the rotation. Not resistance against the rotation. So based on this concept, let us calculate and let us see what is the effective length of different end condition according to the AS 456 2000. So let us calculate effective length of the columns as per IS 456 2000. Right, this is available in your table number 28 of your IS 456 2000. Generally there are 8 conditions are there, but practically we will use some 4 conditions. So those 4 conditions we will discuss in detail here. So here in the column, degree of end restraint resistance of a compression member is given, and symbol how it will look like is given, and theoretical value of that effective length given, and recommended value how much provide in the practically that is given in this table. So here let me see the first case. What is the first case? Effectively held in position and restrained against the rotation in the both direction. Let me define the terms. What is effectively held in position and what is the restrained against the rotation? Effectively held in position means, suppose if you take a column, it has 2 end conditions. So this is one end condition and this is another end condition. That means effectively held in position means this column is supported with some connections. It may be a hinged support or it may be a fixed support. That is true. Effectively held in position means it may be connected with a hinged supports or the fixed supports or a hinged support at the both the ends. The condition may be this may be fixed, this may be a hinged, or this may be a fixed, this may be a hinged, or both condition, both ends are may be fixed or both ends are may be hinged. If we are connecting the both the ends of the column by means of any supports, then we can call that is effectively held in position. So that is the meaning of that. Then coming to the meaning of other word, restraint against the rotation. That means there is no chance of rotation of a column at the both the ends. Means that condition, when we get that condition, already we have seen what is a fixed condition is. So fixed connection, there is no chance of movement in any direction, in the horizontal direction or vertical direction along the rotation. If you take the hinged condition, there is a chance of rotating clockwise or anti-clockwise direction. So here we have a resistance of this rotation. That means this column is connected with two fixed supports at their ends. That's why this meaning of this condition, that is effectively held in position and restrained against the rotation in both ends, nothing but both the ends of the columns are fixed. Right? It look like this. Now if you draw, if you apply a load over this, say P is the load you are applying here, then it will bend like this. So I will draw one more scale L apart from that. So it will buckle like this. So this is a zero bending moment point here, and this is the zero bending moment point. This length will be the effective length. So you can see the clear the difference here. From here to here, there is no movement. From here to here, there is no movement. The movement starts from after some distance from the fixed support. So generally for fixed support, at the supports, the moments are zero. The moments will not get. After some distance, with the beam or column starts to start bending. So this is the effective length. The theoretically this value will be 0.5 times. Here L nothing but it is the unsupported length of the column. What is that? Unsupported length of the column. In formula we have said that capital L, but in the code they have chosen as small l, nothing difference. Here LEF is the effective length and say small l is the unsupported length. Right, unsupported length is given to you. The effective length of this particular situation, theoretically we can use 0.5 times 0.5 of a unsupported length. I can say it is a 50% of unsupported length. Right, 50% of unsupported length. But code says us the effective length for this condition practically you have to provide say 0.65% of unsupported length for this particular case. What is that case? Effectively held in position and restrained against the rotation in both the ends. So let us go for next case. The next case is, see here, effectively held in position at both the ends. That means your column is supported with any of the supports in either ends, but restrained against the rotation at only one end. See, restrained against the rotation at only one end. So I can assume at this particular point it is having a fixed support. So I can say it is restrained against the rotation, and another point here I have say a hinged support. So what it said in the case? One end is restrained against the rotation, another end is not restrained against the rotation. When we get the condition called not restrained against the rotation, when the particular end of the column is supported with a hinged support, then only we get our that end of the column will not be restrained against the rotation. So I am assuming this condition is fixed condition, this is a hinged condition, so there is no restraint against the rotation. So your this will be bent like this. So it is a support simple here. The bending moment 0 will get at the support only, right? And this support hinged support, and for the fixed support after some distance we'll get the bending moment value is 0, right? So you know the effective length of any column is that is distance between two consecutive distance between the 0 bending moment points or point of contraflexure points. So this is the L effective, and this is your unsupported length. According to code, there is a values for this to calculate L effective, that is 0.7 times of unsupported length. This is a theoretical value, but practically code suggests, that is IS 456-2000 suggests us you have to provide 0.80 into unsupported length as a effective length for this case. See here, what is the case? Effectively held in position at both the ends, but restrained against the rotation at one end. That is nothing but one end is fixed, another end is hinged. Like that, we can calculate we can calculate the effective length according to this case number 2. So let us go for case number 3. See here, effectively held in position. I already explained you what do you mean by effectively held in position. Means they are the two ends of the column are supported with any one of the kind of support, that is maybe hinged support or fixed support at their ends, right? But not restrained against the rotation. That means both the ends that there is no resistance for the rotation. You know, there is no resistance for rotation means they are supported with a hinged support at their both the ends. Clear? That's why there is no resistance of rotation here and there is no resistance of rotation here. As it is a simply support, for a simply support we will get the 0 bending moment at the support only. So bending moment is 0 here. Okay, bending moment is 0 here at this point, and bending moment also 0 at other end at the support only. So bending moment is 0 at particular end here, that is 0. Now you know the effective length of any case, that is the distance between the two zero bending moment points. So this is the 2 0 distance between 2 0 bending moment points. It is L effective. Okay, so it is equal to your unsupported length. So the unsupported length is what? L. So I can call here your L effective is equal to unsupported length. That's why they have given the critical value for this is 1 times unsupported length. A practical also we need to provide 1 time unsupported length of the column. So that is L effective equal to L. So let us go for next case or final case. Generally we have 8 cases, but I am explaining here only 4 cases. Those are generally used in our construction. Those important cases I am discussing here. Right. Here effectively held in position. The case is effectively held in position and restrained against the rotation at one end. So at only one particular end we have a restraint against rotation. See the meaning. The effectively held in position and restrained against the rotation at the one end. Only a particular one end only it has a held in position, and at that particular end only it has a resistance against the rotation. Right? And other end it is not resistance against the rotation of the other end. So what do you mean by this? Only one particular end of the column it has a resistance against the rotation, as well as it is held in position. That means only one end of the column it is supported with any one of the support. And as in one more condition as mentioned, the condition is it is restrained against the rotation at one end. That means that support must be a fixed support. But about other end is given that it is neither held in position not restrained against the rotation. So I can call it as that is a what? Free condition. So one end is fixed here, another end is free. So this you can see your what is that? A pole in front of a temples, or you can say electric rigidly fixed electric pole. For electric pole, what one end is say, fixed for this at the ground, and another end is free. That is the best example for this case. So the meaning of this case is one end is fixed, another end is free. Now if we apply a load, so it will deflect like this. And the code has given for this the theoretical value of L effective is 2 times their unsupported length, and practical value also 2 times effective length. So L effective is equal to 2 into your unsupported length, 2 into L. So this is unsupported length, you know, the actual length or height of the column, the distance between the end connections. So like this we can calculate effective length of the column. Okay, so if we want to design a column, we have to substitute the effective length of the column. Effective length can be calculated based on the end conditions. So any 4 of this condition may be given to you. Based on that you can calculate what is the effective length of the column. So let us start discussing load carrying capacity of a short columns which are axially loaded. You know, axially loaded column means the column is subjected to load at this axis of the member. That's why there is a axially loaded column. And we are discussing load carrying capacity of a short column. So what is the definition of short column? So you know we have defined the column, and we have categorized the column as a long column and short column. According to the codal provision, this column should to be a short column, then ratio of effective length to the least lateral dimension is less than 12, then we can call it as a short column. So for this case, what is the load carrying capacity of that short column we have to decide, right? So this is given in class number 39.3 of IS 456-2000. If your short column is provided a lateral ties, you know what is the lateral tie means? is a longitudinal section of the column. So these are the main reinforcement provided in the column, and the lateral ties are provided in transverse direction of the column. See, these are lateral ties. If the lateral ties are provided, then how to calculate the ultimate load resisting load carrying capacity of a short column? Right, the code is given one statement that the ultimate load on the short column with the lateral ties when your E minimum does not exceed 0.05 times lateral dimension, that is E minimum must be less than or equal to 0.05 times least lateral dimension. Say I'm using small d is my least lateral dimension, then we can call it as an axially loaded short column. Then the load carrying capacity of the column, there is a factor load or ultimate load PU is 0.4 into FCK into AC plus 0.67 Fi into ASC. There is no derivation for this. Directly I am taking this formula from IS 456 2000. So let me discuss what are the terms we have here. PU is equal to factor load. It is directly a factor load. When you get the factor load, when you multiply your working load with a partial factor of safety, that is 1.5, then we will get that factor load. And here the term AC is nothing but area of only concrete. AC nothing but what? Area of concrete. And how to calculate this? Once you know the gross area of the section, suppose if you have the rectangular cross section of a column, you know this is a B and this is a this is B and this is D. The gross cross section is equal to area, that is B into D, right? B into D. So if you deduct the gross cross section area minus area of steel, that is ASC, area of steel, longitudinal reinforcement, deduct that, we will get what is the area of concrete alone. And you know FCK is a characteristic compressive strength of a concrete. So there is a terms, if you substitute all those values, this AC, ASC, FCK and Fy values in the formula, we will get what is the ultimate load carrying capacity of a axially loaded short column with what is that condition when it is provided with a lateral ties. What is that? Lateral ties. Then we have for the same column, if it is provided with a helical reinforcement, if it is provided with a helical reinforcement, the same short column, if it is provided with a helical reinforcement, then that factor, that ultimate load what we calculated in the previous case should be multiplied with a 1.05 times. From this I can say the load carrying capacity of a helically reinforced column is 5% more than, is greater than 5% more than your load carrying capacity of column which is laterally tied. So that is the meaning of this. That's why to calculate when a short column helically reinforced, then the load carrying capacity of that particular column can be calculated by using formula PU is equal to 1.05 whole multiplied by 0.4 FCK AC plus 0.05 Fy into ASC. You know FCK is characteristic compressive strength of a concrete, ASC is the area of a concrete alone, Fy is yield strength of a steel, ASC is area of longitudinal reinforcement provided in the column. Right? This is how we calculate. And there is one more codal important provision, that recorded in clause number 39.4.1 of IS 456. The ratio of volume of helical reinforcement, that is VH, to the volume of core VC shall not be less than this value, that is VH by VC shall not be less than, that is 0.36 gross cross section area by area of concrete minus FCK by Fy. So this clause is very important for your competitive exam purpose as well your design of this short column also. So let us start solving or the calculating the load carrying capacity, or the I can say load carrying capacity means what? Indirectly it is a strength of the column by solving some problems. So here the problem is like this: a rectangular RCC column of size 350 mm by 250 mm Here don't confuse, we have to follow B into D notation. So this is a B and this is a D for this column, right? Size, the reinforced with how many bars? 6 bars of 16 mm dia, and the grade of steel is 415, grade of concrete is M20. The effective length of the column is 28 meters. They are not given here the condition on which your column is mounted, but they directly given what is the value of effective length. For that, what you need to calculate? Determine the maximum permissible axial load on the column. That is load carrying capacity of a column. So what type of column we can decide based on the shape? It is a rectangular column. And size of the rectangular column is B is 350 mm and D is 250 mm. And the longitudinal reinforcement provided is 6 bars of 16 mm dia. And the clear cover we have to assume is say 40 mm. And effective length LE given is what? LE is equal to RLEF is equal to how much? To 2.8 meters, that equal to 2800 mm. So this is the cross section of that particular column. The 350 mm is B and 250 mm is D, and this gap what we have between your ties and the face of the column is a cover, that equal to 40 mm. For by considering this, we can calculate what is the load carrying capacity of a column. For that, what we required? We required what is the ASC, area of steel, area of longitudinal reinforcement, and area gross area of the cross section of the column, right? A grade of concrete and grade of steel. C, a grade of concrete given is M20, that is FCK 20 Newton for mm square, and grade of steel is Fe 4 and 5, so Fi equal to 4 and 5 Newton for mm square. And we need to calculate gross cross section area, that is multiplied by cross section B into D. Here B is 350 and D is 250. If you multiply this, we will get 87500 mm square. And we need to calculate what the total area of reinforcement is. So we can calculate number of bars given and area of 1 bar. Number of bars are given 6 bars, and area diameter of one particular bar is 6, that is 16 mm. So pi by 4 into 16 square will give me the total area of cross section of a longitudinal reinforcement, that is 1206.14 mm square. So now I got everything except area of concrete alone. You know how to calculate area of concrete alone? Area of concrete alone is AG minus ASC, that is gross cross section area minus area of reinforcement provided in longitudinal direction, that is 87500 minus 1206.14. If you get that, area of concrete alone will get is 86293.86 mm square, and he has given L effective is 2.8 meters, that equal to 2800 mm. Now we have to decide whether we need to calculate the load carrying capacity of a long column or short column. It does not mention in the problem whether it is a long column or short column. That column we have to decide as whether it is a long or short based on your slenderness ratio. You know the slenderness ratio nothing but effective length of the column by least lateral dimension. So effective length of the column is what? 2800, and least lateral dimension means in B and D, what is the least dimension? Your D is the least dimension, that is 250. That value we have to substitute here, 250. So we'll get 11.2, which is less than 12. So according to the code, if L effective by least lateral dimension is less than 12, we can categorize it as a short column. So now we have to calculate the load carrying capacity of a rectangular short column, which is laterally tied with a lateral tie we have to provide here. Is not mentioned helical or lateral, so we can assume it as a lateral tie. For that, calculation of strength or load carrying capacity of a column, the code has given formula. What is that? 0.46 FCK into AC plus 0.67 FY into ASC. So 0.4 FCK is 20. ASC is already we have calculated area of concrete 86293.3 and 0. FCK, right, and here Fy is 415 and ASC is area of longitudinal reinforcement provided in the column. If you solve that, we'll get 1025714.11 newtons of the load carrying capacity of column, if we convert that into kilonewton, that is 1025.71 kilonewton as a strength of that column. I can say load carrying capacity of that column, right? So this is how we calculate load carrying capacity of a axially loaded short column. So let us solve one more problem. A short column of size 400 mm by 400 mm is reinforced with 4 bars of 25 mm dia, and the column is 5 meters long with both ends are effectively held in position and restrained again in any direction. So you know what is the meaning of this? Find the axial factor load of column can carry, and the material used for this is M20 grade of concrete and HYSD bar. So it is a bar of steel. So it is a bar of steel is HYSD. So according to this, the given that it is a short column, so we need to go for checking the slenderness ratio, and from the dimension of this column, we can decide that the cross section of column is 400 by 400. So B equal to 400 and D equal to 400. So it is a square column, and that what is that? 4 bars of 25 diameter provided, and they are given unsupported length of the column. So capital L is equal to what? 5 meters, and they have given condition for calculating effective length of the column. What is that? Both ends are, say this is a column, say column, both ends are effectively held in position and restrained against the direction. That means they are restrained against the rotation in both the direction, both the ends. So when they have restrained against the rotation to both the end means what? They are fixed at the both the end. So this end of the column is fixed and this end of the column also fixed. Then we need to calculate what is the effective length of the column. So this is how we calculate effective length of the column. So this is the what is the bulking, or I can say bending parameter, bending direction of the column. This will give me the L effective LE. So according to the code, we know when this condition occurs how to calculate L effective. Right? This L effective equal to what? According to the code, that is half of your unsupported length, or I can say 50% of your unsupported length, L by 2. So L by 2 is 2500 by 2. So then we can calculate what is the effective length of the column. That equal to what? 2500 by 2 will get somewhere around 19. We'll get some 1750 like that. Say to calculate area of steel now. The area of steel is 4 bars given, 4 bars of 25 mm diameter. So 4 into pi by 4 into 25 square will get ASC is area of a steel provided longitudinal direction, that is 1963.5 mm square. And area of concrete is AC equal to AG minus ASC, that is gross cross sectional area minus ASC, that is 400 by 400 minus 1963.5. Then if you get we will get 158036.5 mm square. So then you can calculate factor load. Okay, the P equal to 0.4 FCK AC plus 0.67 FY into AC. Now substitute those values. 0.4 FCK is 20, AC is 158036.5, and 0.87 Fy equal to 415, AC equal to 1963.5. Then if you simplify this equation, then we will get the total load, the factor load is 1810.24 kilonewtons. Right, let us discuss one more problem. Here, a circular column of, it is problem on circular column. The diameter of the circular column is 300 mm, reinforced with 8 numbers of 16 mm diameter bar, longitudinal bars were provided. The grade of steel is Fe4 and 5, and 8 mm diameter bar used for a circular rings here. What is that? Circular rings at 250 mm pitch length. The length of the column is 4 meters, and they have given condition here. It is effectively held in position at both ends and restrained against the rotation at only one end. That means one end of the column is fixed, another end of the column is hinge. For that condition, we need to calculate effective length is. So the area of concrete is M20 grade, and determine the safe compressive load that could be applied on the column excluding sulfate of the column. So let us see, this is a circular column, right? The diameter of circular column is 300 mm. The longitudinal bars are provided is 8 numbers of 16 mm dia. So the circular ties are 8 mm dia, either placed at a 250 mm pitch, and the Fy equal to 415 Newton per mm square. Fck is 20 Newton per mm square. So this is a cross section and end condition. So this is a column, as they are given that one end of the column is fixed. That means they are they are having restraints against the rotation in one end, and they are not having restraint against the rotation at other end. So one end is fixed, another end is free. So and then unsupported length given is L equal to 4. For this we need to calculate LEF. So it is a cross section of that column, and is 8 numbers of 16 mm diameter bars are provided, and the pitch length is 250 mm center to center. Clear? So let us calculate gross area of concrete AZ, as it is given a circular column. So pi by 4 into d square, diameter of the column is given 300 mm. Then we will get AZ equal to 714.29 mm square, and total area of longitudinal reinforcement equal to number of bars provided by area of 1 bar. Number of bars is n. Pi by 4 d square is the area of 1 bar. If you substitute 8 into pi by 4 into d square, you will get area of steel in longitudinal direction is 1609.14. Now we need to calculate area of concrete, that is AC. If you deduct gross area of column minus area of steel, we will get the gross area of concrete, that is 69105.15. Right now, unsupported length, we know when it is effectively held in position at one end and restrained against rotation at another end, the L effect is 0.8 times L. This is we can get according to the IS 456 2000. So 0.8 into L is 4000, we get 3200 mm. Clear? So the slenderness ratio is, we don't know what type of column it is, either short column or long column, that we can decide based on the slenderness ratio, that is L effective the least lateral dimension. So L effective is 3200, the least lateral dimension is say 300 mm. So this is the 10.67, which is less than 12. So we can decide is the short column, right? The strength of the column can be calculated Pu equal to 0.4 FCK AC plus 0.67 Fy ASC. Now substitute 0.4 is 0.4, FCK is 20, AC is 69105.15, 67 is 67, Fy is 415, ASC is 1609.17. If you simplify that, we will get 1000.26 kilonewton as a load carrying capacity of a column. There is a factor load. What he asked in problem? The safe load excluding the sulfate of the column. So let us calculate what is the safe load is. So Pu is what? Factor load or design load. It can be calculated working load by multiplying factor of safety. So I can write Pu equal to P into partial factor of safety. So this is the working load or safe load that we can apply on the column. That is Pu is 1000.26 equal to P into 1.5. If we want to calculate P, that is 1000.26 by divided by partial factor of safety 1.5, we'll get 666.84 kilonewton is a safe load. It is including sulfate of the column. So next we have to calculate, deduct the sulfate of the column. Then we can calculate what is the safe load to be applied. For calculating sulfate of the column, that is volume of column multiplied by density of the material. So volume of column can be calculated area of column, cross section of column, and length multiplied by density of the material. And is RCC, we know that 25 kilonewton per meter cube is that density of the column. So pi by 4 d square, d is a 0.3 meter diameter, and this is 4 into 25. We get PS. Only what is this PS? Sulfate of the column. So we know the total load nothing but applied load plus sulfate of the column. So if you deduct the from total load, what is the sulfate of the column, we'll get what is the load can be applied. So PA equal to P minus PS, that is 666.84 minus what is that 7.07, we'll get 659.77 kilonewton. So sulfate of the column is PA if after deducting the self-weight of the column, the safe compressive load that could be applied on the column is PA equal to 659.77 kilonewtons. So thank you. That's all for today's lecture.